Hello, welcome back. So today we're going to continue our discussion on the definite integral. Recall from yesterday, if we want to find the area between a curve or a function and the x-axis, we use this definite integral right here. We use this little symbol. And yesterday we mentioned, or in a previous video, we mentioned that this is what we call an integrand. And what the integrand does for us is it sums up an infinite number of rectangles. That's all this does. So if I have a function here and I want to find the area between A and B, and we talked about this yesterday, I can find the area by partitioning this up into really tiny rectangles. The more rectangles we have, the more accurate our area will be. But the problem is, if I look at one rectangle here, if I look at just the one rectangle, it has a width delta x and a height of f of x. So I can get my area by saying it's going to be f of x delta x. But as we said yesterday, we're going to let delta x go to 0. And we get something special, and we say this: if delta x goes to 0, we get dx, the tiniest, smallest width of a rectangle that this can be, which is basically 0. And that's how we get this definite integral right here. So when we're looking at a rectangle, this is our length, and that's the width of our rectangle. We can use this to solve for the exact area, but we can also use it to write an area problem, and that's what we're going to be doing today. We want to write a definite integral that can be used to find the area of some shaded regions here. So the first one we have is a parabola. We're looking for the area under this parabola from 0 to 3. And I can look at that. There's 3. I can find this area pretty easily. So ideally what we want to do, though, and we're going to talk about this more later on, let's draw a Riemann rectangle somewhere in there. There's my Riemann rectangle. Now, if I were to look at this rectangle right here, I know it has a width of delta x. But remember, this is really tiny. I blew it up, but this is really tiny. It's basically 0. So therefore, we just really call it dx for short. Get it? For short, because it's really small, it's short. Over here, we still have our function, f of x, the height of our function, whether we use a left Riemann sum or right Riemann sum, or the midpoint Riemann sum. If I wanted to now find the area of just my one rectangle, I'm going to write that as f of x dx. But remember, this is only the area of one rectangle. I have an infinite number of rectangles that we want to add. So what adds up an infinite number of rectangles? That's what our definite integral does. So I'm going to write this as a to b. Now I can change all of this, of course, because what is f of x? It's our x squared plus 3 dx, and our domain goes from a to b, or 0 to 3. And this integral will find us the exact area under the curve. Now, we're not solving this just yet. Right now we can approximate it, but we're not solving it just yet. That's for something later on for us. All right, so let's take a look at number 2. For number 2, we have the absolute value graph here from -3 to 3, and we want to write the integral. So again, the area formula for this. So once again, if I draw my Riemann rectangle, remember this rectangle, if I draw it off to the side, has a width of delta x and a height of f of x. And remember, it's not really delta x, we should write it for what it really is going to be, dx. So dx, remember, is the width basically 0. So this area of this rectangle is really 0 right here. So if I now want to find the area, my f of x is just as 3 minus the absolute value of x. So I'm going to write that out, 3 minus the absolute value of x times dx, the length of my rectangle times the width of the base. And that's one rectangle, so to get all of them, we have to integrate this. That's what we call it integrating. we're going to sum up an infinite number of rectangles. That's what this does. This is now going to add up all those rectangles, an infinite number of them. Now, and this is going to go from -3 to 3. And you can actually use symmetry for this later on, we'll talk about. But I can go from 0 to 3 and then just double it, but we'll talk about that later on. So let's try number 3 right here. We want to find the area from 4 to 7. Well, there's 4. There's 7. So there's my rectangle. So I can draw my little rectangle of mathematics here. And there we have it. It has a width of dx and a height of 1 over x minus 3. There's my rectangle of mathematics here. To get my area, I'm going to take this 1 over x minus 3 multiplied by dx. Length times width. And we're going to integrate that from 4 to 7. That's actually how we say we're going to integrate that from 4 to 7. So this is going to give me the exact area. Now again, do I know how to find the exact area yet? No. That's something for January for us we'll talk about. Right now, that's just going to be our answer right here. So for number 4, oh no, this time it's different. It's terms of y. Oh, that's easy. That just makes our rectangles horizontal. We're just going to make a horizontal rectangle. Everything's the same. There we go. We want to go from 0 to pi, so 0 to pi on the y. So there's my rectangle, and again, it's going to be dy this time and have a width of sine of y. So if I want to get the area, it's going to be sine y times dy, and we're going to integrate that from 0 to pi. And there's our answer. So easy, a senior in May better be able to do this. All right. So very easy to write an area formula. In the next section here, now we're going to want to go ahead and see, hey, can we actually solve some of these? Now, most of these we won't be able to solve, like question number 3, anything curvilicious right now, we're really not going to be able to solve for them exactly just yet. But there are some we actually can, because remember, what does the integral find for us? If we're looking at an integral, remember, this just finds for us area under f of x, under the function f of x. So if I take a look at a question like number 5, I want to find this area here. Now this is very similar to what we did yesterday. What I can do here, I can graph this. This is the function y equals 4 on the domain 1 to 3. If I were to graph this, this is the line y equals 4 on the domain 1 to 3. And if I were to look at the area just under that domain, I recognize something. That's just a rectangle. Well, that's easy. I know the area of a rectangle is base times height. Therefore, I can say my area from 1 to 3, 4 dx is just a base. The base here is going to be 2, be careful, times the height, which is 4. And that's going to give me 8. And there's our answer. So if I know the shape, and know the shape in this area, I can just use my geometry formulas. That's what this is saying right here. For a question like number 3, same idea. X plus 2, well, that's just a line. I can graph a line. There's 2. I want to get the domain from 1 to 3. And this is just a trapezoid. Area of a trapezoid, you're going to memorize this one. 1/2 the sum of the bases times the height. So how do I get my area here? 1/2 my bases. So you ready? At 1, this base is going to be up 3, and then at 3, this one's going to be at 5. So it's going to be 1/2 3 plus 5 times, this is the height, and that's going to be 2. You might be thinking, well, why is the height 2? Well, in a trapezoid, the bases are always parallel to each other. And if I simplify this again, I just get 8. Number 7, we're going to recognize this one. We always graph this one. This is a circle. And for circles, we always graph. Even though we can solve a lot of these later on, we're always going to graph a circle. So this is a circle, and it's the top half because this is positive. We're going from -2 to 2. And the question is, well, what's the radius? Well, the radius is just 2, because remember, it's going to be this. It's y equals the square root of r squared minus x squared. My radius is being squared here. My radius is just 2. Area of a circle, just memorize it, 1/2 pi r squared. We get 1/2 pi. Well, my radius is 2. Square it, we're going to get 2 pi. Make sure you simplify. Don't leave it like this. Don't leave it as pi, 2 squared. You want to simplify that. Okay? All right. I hope you guys enjoyed this video. Go on to video number 2. We'll take a look at a few more examples. I will see you then.